Hi, we are starting Unit 7, and in this unit we're going to be looking at how to use calculus to graph functions. So using what we know about the derivatives, we're going to be able to do some much more accurate graphs of much more complex functions than what we were able to do with just transformations in the advanced functions course. So the first day in this unit is talking about increasing and decreasing. So an important thing to be able to identify in our graphs is where functions are increasing and decreasing and graph that accurately. That in turn can also help us find the maximum and minimum values in a function. If we know a function is increasing to a point, then decreasing after, that's going to be a value that's a maximum, and vice versa for a minimum. So the first thing we're going to do here is to just define what increasing and decreasing functions mean. And I know that you guys will have a good kind of conceptual understanding, even right from when we started linear graphs in grade 9. Increasing goes up, decreasing goes down. But the kind of formal mathematical definition of that tells us that in an interval for any two numbers x1 and x2, if x2 is bigger than x1, so these are in order, x1 is the smaller x value, x2 is the bigger one, that f at x2 must be greater than f at x1 for all values in that interval. So the function is increasing if every subsequent x value has a higher y value than all of the smaller x values than that one. The opposite of that is decreasing functions. So again, if x1 and x2 are x values in the interval, and x2 is the larger of those two values, that the y value corresponding to that must be lower than the y value of the previous or smaller x values. So an important thing when we're looking for our intervals of increasing and decreasing are where those intervals can switch or where the endpoints of those intervals might be. So we're going to find those at what's called the critical numbers, the zeros and undefined points of f prime. So those are the values that we've been testing all along. This is very, very similar to the optimization questions. We're just now going to apply it to using the same knowledge that we have about finding max, min, and where it's increasing and where it's decreasing, a little bit more formally mathematically, to give really accurate graphs of different functions. So these critical numbers are basically anywhere that f prime would equal 0 or where f prime is undefined. And we're going to check the intervals around each of those critical numbers to determine where it's increasing or decreasing. The only way a function can switch from increasing to decreasing or vice versa is for somewhere in the middle for the derivative to equal 0, for instance, like at a turning point, or for the derivative not to exist, which might happen at an asymptote, or it might happen at a cusp, or some other kind of example like that. So I'll just kind of sketch this out. We know just kind of a basic graph there. So this would be an interval of increase, and this is an interval of decrease. So we know at this turning point, f prime at x equals 0. And the undefined points might be an asymptote, might be a cusp, might be something else happening there. But maybe just a kind of graph like that. So here, again, we're going from increasing to decreasing, but this is a different kind of situation. Somewhere in the middle here at this asymptote, f prime at x does not exist. So it can change from increasing to decreasing where the derivative doesn't exist or where the derivative equals 0. There's one more kind of example that is a little bit maybe less likely to be thought of because the derivative cannot exist at a cusp. So if you have a graph like that, this would be a point where the function exists, but the derivative does not. So here we've got another example of where the derivative would not exist, but it would go from decreasing to increasing, or it could be the opposite, increasing to decreasing. So those critical numbers are really important. We're going to be finding those and figuring out where they are and checking the intervals around them to figure out where those intervals of increase and decrease are. So critical numbers is, again, just a more formal mathematical definition. Critical numbers happen where f prime at c equals 0 or f prime at c doesn't exist. Small kind of terminology thing. A critical point is the xy pair that x is a critical number. Now, obviously, sometimes this might not happen if a critical number is an asymptote. You don't have a critical point there. But just the kind of difference here, if it says critical number, you're looking just for the x value. If it says critical point, you want the whole coordinate pair if that y value exists on the function. And our first example here, we want to find the critical numbers for f prime at x equals x squared plus 3 over x minus 1. So we're going to first find the derivative and then check the derivative to find where those critical points are, critical numbers. So my derivative using the quotient rule, f prime at x is the denominator, x minus 1, times the derivative of the numerator, which is 2x, minus the numerator, x squared plus 3, times the derivative of the denominator, which is 1, all over the denominator squared. So the first step to finding critical numbers is always finding the derivative and simplifying. This is really why we put so much emphasis on factoring the derivative fully in those first units, because a lot of what we do with our derivatives is figuring out where they're equal to 0. So I get 2x squared minus 2x minus x squared minus 3 over x minus 1 all squared. So x squared minus 2x minus 3 over x minus 1 squared. And then again, I don't know if this is going off the screen, factor here the numerator. So I get x minus 3, x plus 1 over x minus 1 squared. So when I'm listing out my critical numbers, I actually like to specify, so I'm finding my critical numbers, I'm going to specify I'm looking at both where the derivative equals 0 and where the derivative does not exist. So I'm going to list that out for both kind of different cases, and then I'm just going to list my x values for each. So where would this equal 0? At 3 and negative 1. And then where doesn't it exist? Where the denominator would equal 0 or there'd be any restrictions, and that's x equals 1. So these are all potential turning points of this function. So here we've got an asymptote, probably looking at our original function, we've got an asymptote at x equals 1. So it could change increasing to decreasing or vice versa around that asymptote. And we also have critical numbers that might be max-min points at 3 and negative 1. And I'll show you in a later example how to check those. Okay. Now, this is just kind of, I think, probably review of your understanding here. We need to test whether things are increasing or decreasing based on the sign of the derivative. So if you can take the derivative for all values in an interval, and we know we're excluding those values of where the derivative does not exist because those are our critical numbers. So we will be testing intervals between the critical numbers. If the derivative is negative, that means that it's decreasing. And obviously, if the slope of the tangent is negative, the function's going down. If the derivative is positive, the function is increasing. If the slope of the tangent is positive, the function's increasing. And then lastly, if the derivative equals 0, then it's constant. So it's not increasing or decreasing at a point where the function equals 0.